present the lecture Engineering Thermodynamics. First of all, we are going to see about what is thermodynamics. Thermodynamics is nothing but a science of energy transfer. Mainly it relates the transfer between heat and work, and also the properties of the system. The example for thermodynamics application is power plant, IC engine, refrigerator and many other devices. The thermodynamics is applied in many fields. In day by day we are using lot of devices which is based upon the thermodynamics. Here I am giving two examples. One is power plant, another one is IC engine. The power plant, in which the heat is supplied to the boiler. Here the water converted into steam, and then the steam goes to the turbine where we get the work. So here what happens means the heat energy in the steam converted to work energy in turbine. From that simultaneously we are getting power. In the IC engine what happens means we are supplying fuel. After the burning of fuel, it will produce hot gas. This gases pushes the piston and then producing the work. So here also the heat energy from the fuel converted to work in the IC engine piston. So these are the some of the example in the thermodynamics. Then thermodynamic system. A system is nothing but a closed region in which our attention is focused. In any place, any region within the boundary, we can say that it is a system. Then surrounding. What is surrounding? The surrounding is nothing but anything other than a system are called surrounding. The boundary is nothing but the partition layer which separates system and the surrounding. So here we see the three important parameters. One is system, another one is surrounding, third one boundary. So these three are linked between each other. Types of system. There are different types of systems are there. Mainly open system, closed system, isolated system. Here these three systems are classified based upon the mass and energy transfer. If the mass and energy transfer takes place between system to the surrounding and the surrounding to the system means it is called open system. If there is no mass transfer but there may be energy transfer means it is called closed system. In isolated system there is no mass or energy transfer. Properties. The properties are the coordinates to describe the condition of a system. Example, temperature, volume, pressure and some other things. Then state. State is nothing but in the particular condition of the system is called state. For example, we can say that the liquid state, solid state, gaseous state. So mainly we say that these three states. So state is nothing but the particular condition of the system is called state. Process. The system changes from one state to another is called process. For example, if we heat the water means then it converted into steam. So from liquid state to gaseous state we got by using water. So this is called process. Simply we say that we are heating the liquid. So the heating process takes place. And also in the process, the cyclic process is nothing but the initial and the final state of the system are identical is called cyclic process. Cyclic process means repeatability. Wherever the starting point is equal to the end point, the initial and final state are equal or identical. It is called cyclic process. Then equilibrium. What is equilibrium? Equilibrium is the same level, the same condition, like that we told that equilibrium. There are different types of equilibrium are there. One is thermal equilibrium, mechanical equilibrium, chemical equilibrium. What is thermal equilibrium? Thermal means simply we say that the thermal is nothing but temperature. The temperature should be same throughout the system. Then we say that the system is in thermal equilibrium. Mechanical equilibrium. Simply we say that mechanical means related to force or some effort, or let us consider pressure. So here what we say that the mechanical equilibrium is nothing but the unbalanced force should be absent. That means there is no unbalanced force existing in the system or surrounding, or between system and surrounding. Then it is called the system is in mechanical equilibrium. Chemical equilibrium. So chemical means simply we say that reaction. The reaction relates chemical equilibrium. So here the chemical equilibrium is nothing but in the system there is no chemical reaction takes place, and also mass transfer also not takes place between system and surrounding. Then it is called the system is in chemical equilibrium. So here we are seeing three equilibriums. One is thermal, second one mechanical, third one chemical. So it relates temperature, unbalanced force and chemical reaction. So these are the property related to this equilibrium. From that three equilibrium, we may conclude the system nature in thermodynamics. What is thermodynamics? The thermodynamics is nothing but a system is in thermal, mechanical and chemical equilibrium. Then the system is called as an thermodynamic equilibrium. So once the three equilibrium are existing in the system, then we say that the system is in thermodynamic equilibrium. Dynamic is nothing but the property related to the movement or motion. Thermo, already we saw that thermo nothing but it relates to temperature. So thermodynamic equilibrium includes these three type of equilibrium: thermal, mechanical and chemical equilibrium. Thermodynamic process. So already we saw that the process is nothing but the system state changes from one condition to another condition. Then it is called thermodynamic process. But there are different types of process are there. When the process takes place in constant temperature condition means it is called isothermal process. If the system properties changes in constant volume condition means it is called isoporic process. If the system pressure maintain constant and the process takes place means it is called isobaric process. In the system there is no heat transfer takes place between system and the surrounding, and also surrounding and system, then it is called adiabatic process. If the system undergoes the process in general is called polytropic process. Here we can represent different process in terms of the polytropic index, adiabatic index. In general, adiabatic index value is 1.4 and the polytropic process index other than 1.4. It is called the polytropic index. So these are the some of the process. Here in each process the properties will be varied. For example, the change in heat transfer, change in enthalpy, change in entropy, these are all varying and it has separate formulas for each different process. Okay, next the important topic in thermodynamics is laws of thermodynamics. There are majorly three laws governing thermodynamics apart from the third law. The first law is zeroth law, second law is first law of thermodynamics, the third one is second law of thermodynamics. In zeroth law of thermodynamics, it based upon thermal equilibrium. Already we saw in previous slides, thermal equilibrium is nothing but there is no change in temperature between system and the surrounding. Then the system is called as in thermal equilibrium. So here once again remember that thing. So in zeroth law, what it represents means if two bodies are in thermal equilibrium and a third body is in thermal equilibrium with any one of the first two bodies, then it can be inferred that all the three bodies are in thermal equilibrium. So here in the picture, what it shows means the body A makes thermal equilibrium with B and separately thermal equilibrium with C, then the body B and C are in thermal equilibrium with each other. So as per zeroth law of thermodynamics, we can say that the body B and C are in thermal equilibrium with each other. So this is the concept behind this zeroth law of thermodynamics. So the application of zeroth law of thermodynamics is thermometer. So thermometer here, depending upon the level of the heat, the mercury level will be increased. So we are including three properties. The three properties are in equilibrium. So based upon the zeroth law, this thermometer functioning, work and heat. Before going to the first law and second law of thermodynamics, we must know about the work and heat definitions. What is work and heat? The work and heat both are two forms of energy that can be transmitted. For example, work can be converted into heat, heat can be converted into work. In the first slide already I told that in thermal power plant the heat energy converted into work, and also in IC engine the heat energy converted into work. Like that the work is also converted into heat. So these two are the energies in transfer, in which separately the heat is defined as the energy transferred from one body to another body by virtue of temperature difference between the two bodies. The heat will flow from a higher temperature region to lower temperature region. So here I want to insist one thing. The heat always flows from higher temperature to lower temperature automatically, but the heat will not be transferred from lower to higher temperature without any extra input supplying. We must give some input work, then only it will be possible. So this is the nature of the heat energy. Then internal energy. The internal energy, the name itself, it represents the energy stored within the system during the process. Is called internal energy. So it represents the energy associated with relative molecular translation, molecular rotation, vibration, binding energy, etc. So these are the some definitions about the work, heat and internal energy. So already we saw about the first zeroth law of thermodynamics. Here we are going to see the first law of thermodynamics. The first law of thermodynamics just it discusses about the conversion of work and heat. So already we know that the work can be converted into heat as well as the heat can be converted into work. So this law deals about the conversion of these two energy. So here the first law of thermodynamics, there are two different cases. One is for cyclic process, another one is for change of state. For cyclic process, what it says means, if any system is carried through a cycle, then the summation of the work delivered to the surrounding is proportional to the summation of the heat taken from the surrounding. So we know that the cyclic process is nothing but the initial and the final state of the system are identical. So this is the nature of the cyclic process. So in cyclic process, the equation governed is integration of dW is equal to J into integration of dQ. So we say that the work is proportionally connected to heat, but if we equate two things, means we have to put proportionally constant. So here we are adding the constant J nothing but joule. Here J nothing but joule. It is one of the constant. Here we are using for equating these two factors, work and heat. Normally in the mechanical equivalent of heat is 1 kilojoule per kilonewton meter. This is the value for 1 joule, mechanical equivalent of heat. Then for change of state, it represents the Q is equal to tau plus du. What is Q? Q nothing but the heat transfer or heat energy, tau nothing but work, du nothing but change in internal energy. So in the change of state, it says the complete conversion of heat into work will not be possible. There may be some energy will be stored within the system or accumulated within the system. Is called first law of thermodynamics for the change of state case. So here first law mainly focused on two cases. One is for change of state, another one is for cyclic process. But both are related to the work and heat transfer. Then law of conservation of energy. The law of conservation of energy based upon the first law. Here it says the energy can neither be created nor destroyed if mass is conserved. So it explains the energy cannot be created or cannot be destroyed, but it can be transferred from one form to another form. Yes, already we saw in many slides in this presentation, the heat converted into work and work converted into heat, but we cannot destroy or create. So this is the concept behind this conservation of energy. Here it added further, if Q is equal to 0, tau is equal to 0, then del U is equal to 0. It says that the heat transfer, work transfer 0 means automatically the internal energy also 0. Perpetual motion machine of first kind. So perpetual motion machine of first kind, it is nothing but here imaginary machine. Actually it is not possible. It is an imaginary case for first law. Based upon first law, it is an imaginary case, perpetual motion machine of first kind. It shows it is impossible to construct an engine which produces work without taking heat from the surrounding. It says that it is impossible for the engine to produce the work without the heat input. Yes, it's a true. But if it is the case, means it is called perpetual motion machine. Here again added explanation is there is no input means we getting output. It is not possible. So this is the explanation given in perpetual motion machine of first kind. An engine which can produce the work without taking heat from the surrounding. It is called PMM1, perpetual motion machine of kind 1. But it is not a possible one. Then based upon the first law, we arrived steady flow energy equation. What is steady flow? The flow should be steady. The mass should be, the rate of change of mass should be equal in all places. Then it is called steady flow case. The devices which are found in steady flow is called steady flow devices. So we are using first law of thermodynamics and we derive this steady flow energy equation. Here in this picture what it represents is, here it is control volume, and let us consider this the steady flow device. Let us consider the mass m flows entering and also leaving. The Q is the heat supplied and tau is the work delivered or work we get. And also the inlet is represented by 1, exit is represented by 2. Here the energy entering is equal to energy leaving. In steady flow cases, energy entering is equal to energy leaving. That means the total energy must be constant at different places. Before deriving the equation, we must know about individual parameters. So here we are going to see the parameter U, that is internal energy, P pressure, V volume, G gravitational constant, Z potential head, capital V velocity. So these are the terms which represented related to inlet and outlet. So as per this equation, based upon the condition of energy entering is equal to total energy leaving, we arrived at the equation summation of internal energy, flow work, kinetic energy, potential energy and heat input is equal to the summation of the total energy at exit or total energy leaving. That means the total energy at leaving is nothing but a summation of the internal energy, flow work, kinetic energy, potential energy and the work delivered. So these should be equal. So as per this steady flow energy equation, based upon the concept of first law, it is the final equation which is arrived. It is called steady flow energy equation. The steady flow devices are nothing but a boiler, turbine, compressor and some other devices. So in the previous slide we saw the steady flow equation. Based upon the steady flow equation, we can derive the condition for finding unknown parameters in steady flow device. In the boiler, finally by using the steady flow energy equation, we can find the heat input given to the boiler is equal to mass into enthalpy difference. That means H2 minus H1. H2 nothing but enthalpy at exit, H1 nothing but enthalpy at inlet. It is multiplied by mass, then we get the total heat supplied. So it is the equation derived from the general steady flow energy equation. Then in turbine, already we saw that turbine is nothing but a device which is used to convert the heat energy into mechanical work. It is called steam turbine. Yes, here the equation derived from the general steady flow energy equation. It represents tau is equal to mass into enthalpy difference. But here the enthalpy difference is the difference between inlet enthalpy and exit enthalpy. Since the inlet enthalpy is higher than exit enthalpy, so the enthalpy difference is multiplied by mass, then we get the related work done. So it is also the application of the steady flow energy equation. It is the steady flow device, one of the steady flow device. Then another example is nozzle. The nozzle is also a steady flow device. Here the picture shows the nozzle, and in the cross sectional diagram shows conversion diversion nozzle. Here there are two portions are there, conversion portion, diversion portion. In between is called cross section, and also entrance and exit. Here our main aim is to find the exit velocity. Since normally we know the inlet velocity and the enthalpy of the inlet steam and exit steam, but our main aim is to find exit velocity. It is mainly needed for many cases. So here the formula arrived from general static flow equation is V2 square minus V1 square divided by 2 is equal to H1 minus H2. What is V2 square minus V1 square by 2? It is nothing but change in kinetic energy. It is equal to change in enthalpy. What is change in enthalpy? H1 minus H2. H1 nothing but the enthalpy at inlet, H2 nothing but the enthalpy at exit. So this is the final equation arrived by using the steady flow energy equation. The third device is throttle valve. This is also one of the example for steady flow device. The throttle valve, here the enthalpy should be equal between inlet and exit. This is also the condition getting from steady flow energy equation. Then limitations of first law. What are limitations of first law? We know that the first law deals two cases. One is change of state, another one is for cyclic process. In both cases we deals the heat converted into work as well as the work can be converted into heat. But it gives only the energy balance. It does not mention anything about the direction of energy transfer, whether higher to lower or lower to higher, like that it will not be represented in the first law. So it's one of the drawback. Another one, thermal equipments can be identified only when the direction of energy transfer is known, otherwise it is difficult. And also in the second law gives both energy balance and direction of energy transfer compared to the first law. So here we saw the limitations of first law and the benefit of second law compared to the first law. Before going to see the second law of thermodynamics, we must know about the concept behind the heat engine. The heat engine is nothing but a device which produces the work by consuming heat energy. The IC engine is an example for heat engine. That means the internal combustion is the example for the heat engine. So the heat engine, which includes the heat input, the heat loss and the work delivered. So here there are two reservoirs are there, temperature reservoirs. One is source, which temperature is T1, and another one is sink, which temperature is T2. Source is nothing but a reservoir which supplies the heat. The sink is nothing but the reservoir which absorbs the heat leakage. So this heat engine works between two different reservoirs. So Q1 is the heat input, Q2 is the loss of heat after the conversion of heat into work. Normally the source temperature is greater than sink temperature. From this diagram we say that Q1 minus Q2 is equal to tau u. That means the difference in heat transfer is gives the net work delivered. And also efficiency of heat engine is nothing but output by input. Here what is the input given? Q1. What is the output? Work. So the work may be noted by Q1 minus Q2. So in general the efficiency of heat engine represented by Q1 minus Q2 divided by Q1. So this is the example for heat engine. Here the example is detailedly represented. This picture shows IC engine. that means internal combustion engine. Here what are the components mainly shown here are the cylinder, piston, inlet port, exit port, inlet valve, exit valve, and then spark plug, and then rocker arm, and then connecting rod, crank pin, cam, crankshaft, crankcase, and then crank, and then push rod. So these are the components which are existing in IC engine. So mainly the IC engine is having 4 different processes, that is suction, compression, expansion, exhaust. The fuel entering through the inlet port, through the cylinder, and undergoes process, and then after the heat addition, it made to be expanded, and then finally the waste gases sent to the atmosphere through the exit port. So it functioned based upon 4 processes: suction, compression, expansion, and exhaust. Here mainly we must know that the heat energy in the fuel converted into work energy. So this is the concept behind the IC engine, function of IC engine. So here the IC engine animation is shown here. Here it clearly shows the function of the IC engine, that is through the inlet port the fuel entering, and then it pushes the piston downwards. After filling the fuel, the piston moving from bottom to top, that is BDC to TDC. At the end of the compression, the spark plug delivered the spark, and then the fuel made to be burned. This hot fuel produces the hot gas. This hot gases delivered through the exit port. Before that, it will do the work. So this is the concept behind the function of IC engine. So here this animation clearly explains the working principle of IC engine. In the second of thermodynamics also there are 2 statements. One is Kelvin-Planck statement, another one is Classis statement. Kelvin-Planck statement deals about the engine. Here what it says that it is impossible to construct an engine that operating a cycle will produce no effect other than the extraction of heat from a single reservoir and the performance of an equal amount of work. What it says that for running the engine, definitely it needs 2 reservoirs. Already we saw that one is source, another one sink. But as per this law, it is impossible for the engine to function by using single reservoir. Yes, it is true. For running the engine, it needs 2 reservoirs. So this is the statement which begins Kelvin-Planck statement. The second reservoir, that is sink, is mainly used for absorbing waste heat. So normally no one engine having 100% efficient. So some amount of heat will be losses that goes to the sink. So that we need 2 reservoirs for running the engine. Similarly, perfection motion of machine of first kind, here also perfection motion machine of second kind. It relates the heat engine. It shows the heat engine working in a complete cycle, taking heat from a single reservoir and converting it into work is known as perfection motion machine of second kind. It is not possible. So already we concluded that for functioning of engine, it needs 2 reservoirs. So if the engine running by single reservoir means it is called perpetual motion machine of second kind. But it is not possible. The picture shows the only one reservoir, that is heat source, which is giving input to engine and it produces the work. There is no Q2, there is no second reservoir. So it is nothing but PMM2. Refrigerator. Before going to see the second law in second case, that is Classis statement, we must know about refrigerator. It is a device operating a cycle which will transfer heat from cold body to hot body with some external work. It is meant for cooling down a system. Here what it shows means our aim is to transfer heat from Q2 to Q1. Here the low temperature to high temperature heat transfer will not be takes place automatically, so that we are giving some work input. Here the source temperature is T1, sink temperature is T2. Here the formula behind this COP is equal to Q2 by Q1 minus Q2. What is COP? COP is nothing but coefficient of performance. It is nothing but related to efficiency. Here in the refrigerator and the heat pump we say that COP, not generally efficiency. So it is the formula which shows the ratio between Q2 by Q1 minus Q2. Q2 nothing but the lower heat energy, Q1 minus Q2 nothing but the difference in heat input and output. So this is the formula for COP. Heat pump, it is also a device which is meant for heating a system. It is opposite to refrigerator and air conditioning. Here our main aim is to heat the particular system or space. So COP of heat pump is equal to Q1 by Q1 minus Q2. In both cases, refrigeration and the heat pump, both the formula somewhat related. In COP of refrigerator, the numerator has Q2, that means lower heat energy. In the COP of heat pump, the numerator is Q1, that means here we need the higher heat energy. So it is the output Q1. Otherwise, the both formulas are related, almost the similar characters. Now we saw the class statement. So in second law there are two statements. One is Kelvin-Planck statement, another one class statement. The class statement says that it is impossible to conceive a device that operating in a cycle will produce no effect other than the transfer of heat from a body at lower temperature to a body at higher temperature. So this is the class statement. It mainly focuses on the principle of refrigerator. So the statement what it says that the conversion of or transfer of heat from lower temperature to higher temperature is not possible without giving any input. So for this statement the example is refrigerator. In the refrigerator we are giving work input for transferring heat from lower to high temperature. That means inside the refrigerator cabin to the atmosphere. So this is the example for class statement. Reversible process. What is reversible process? Once a process is possible to run in reverse manner means it is called a reversible process. The reversible process for a system is defined as a process which once having taken place can be reversed and leaves no change in either the system or the surrounding. All natural or spontaneous processes are reversible process. For example, let us consider we are going to heat the water, then what happen? The water converted into steam. Suppose if I remove the heat, that means I am going to condense or cool the steam. Then what will take place? The steam changed into water. So this is the example for reversible process. All natural or spontaneous process are reversible process. Frictionless motion of solids, frictionless and fully resisted adiabatic, isothermal expansion or compression, flow of electric current through zero distance. These are some of the examples. So So the reversible process always not possible. Due to some negative effects, it will not be takes place. Main effect is friction. So due to friction, the reversible process will not be takes place in all the cases. Carnot theorem. What is Carnot theorem? It is impossible to construct an engine working between only two reservoirs which will have a higher efficiency than a reversible engine operating with the same two reservoir. See, Carnot theorem says that the Carnot engine is an imaginary one. It has higher efficiency than a normal reversible engine working between two temperature reservoirs. So it shows the Carnot engine having the higher efficiency in all cases. So this is the diagram which represents the Carnot engine. So here the chart drawn between pressure and volume. So the AB, BC, CD, DA represents the process in the Carnot theorem. That is two isothermal and two isentropic process. Then entropy. What is entropy? Entropy, it is arrived from the second law of thermodynamics. So entropy is the molecular measure of disorderliness. It means the entropy is defined as the ratio between dq by T. What is dq? Change in heat transfer. What is T? Absolute temperature. So this property relates heat and temperature and also molecular movement. Here the Clausius inequality is the continuation of entropy. So it explains whenever a system undergoes a cycle, there are three cases are possible. One is reversible, another one is irreversible, third one is it is not possible. This is a Clausius inequality, that is less than or equal to 0. So for the reversible case, that is integration of dq by T is equal to 0. It means the cycle is reversible. Integration of dq by T is negative if the cycle is irreversible. Integration of dq by T less than or equal to 0, this is known as Clausius inequality. So entropy is the major factor which is used in thermodynamic analysis in many research work. The basic concept of entropy based upon the second law of thermodynamics. So this is the concept behind entropy, and also the entropy will be different for different process. So already we discussed about the different process, that is constant pressure, constant volume, isothermal, reversible adiabatic and Pauli process. In all the process the entropy will be changed, but in isentropic process the entropy will be 0. That is, isentropy means there is no change in entropy. Other process it has its own value, that is own entropy value. So far we saw that the basic things in thermodynamics and the state, cycle, properties, types of equilibrium, thermodynamic equilibrium, and also we saw about different law of thermodynamics, that is zeroth law, first law, second law of thermodynamics, and also we discussed about the application of first law, that means study flow energy equation. It is used in many study flow devices to arrive the final unknown parameters. And also application of zeroth law is nothing but a thermometer, which is used in our day-by-day life. Thermometer, so it is working based upon zeroth law of thermodynamics. And in second law of thermodynamics, there are two devices. One is heat engine, another one is refrigerator. The heat engine is based upon Kelvin-Planck statement of second law. Refrigerator based upon the Clausius statement of second law. So these are the devices which relates the thermodynamic laws. And also in addition to that, we saw that entropy is the property of a system. It has different values for different process, and also based upon the entropy, we are classifying the system into reversible, irreversible, and impossible. So these are the some of the cases in Clausius inequality. Thanks for listening. I hope this session gave the knowledge about basic concept of engineering thermodynamics and the basic laws in engineering thermodynamics and the application of study flow device, study flow equation, and then the devices related to zeroth law, first law, and second law. And also we saw that the entropy, that is the continuation of the second law of thermodynamics. So these are the topics we discussed so far. So thanks to all once again for the listening this video. Thank you so much.